Probably we need to turn off the front light.
No, you can't, because you're being taped.
Okay.
Sorry. Hi, welcome everybody. Thank you for coming to the Distinguished Seminar Series. It's a pleasure to have here today Dr. Giannakis. Dr. Giannakis went to, he got his BS degree from University of Athens in 1981, and then subsequently went to University of Southern California, where he got his MS and PhD, and MS also in statistics. And he has currently an endowed chair, an ADC chair in wireless communication at University of Minnesota. Actually, Professor Giannakis is a man who needs no introduction. He's very well known in the field. He's published hundreds of journal papers and conference papers. He's a fellow of the IEEE. He's currently a distinguished lecturer, IEEE distinguished lecturer. He's received many awards from the Signal Processing Society as well as Communication Society, including the Marconi Award, as well as the URSIP Technical Achievement Award and the SP Society Technical Achievement Award. So, I could go on for a whole hour, basically describing his achievements. It's a pleasure to have you here. Thank you for coming, and the floor is yours.
Thanks a lot, Hamid. It's my pleasure to be here, see you all again, and talk to you about the snapshot of the research carried out in my group. We work on things related to wireless networking, wireless communications, and this one is at the interface of distributed signal processing and wireless sensor networks. I want to acknowledge three of my students that over the last couple of years contributed to this work, as well as a colleague from the CS department. He's a robotics expert, and he gave us, we collaborated on real data collected by sensors mounted on a team of robots. And I want to acknowledge the financial support from the RLCTA grant, and actually part of the work reported here was funded also by the ARO next door, and it so happens that my program monitor is in the audience. So, let me start with the motivating setup. People debate as to the gamut of applications of wireless sensor networks, but almost everyone agrees that they have to be these small devices, relatively inexpensive, that have to operate under stringent power and bandwidth constraints, and they got to have somewhat limited computing capability. And they can perform, they should be also application specific, their deployment and design. And the application I want us to think about today is that of distributed estimation. For example, parameters for habitat monitoring, or levels of gas release, or distributed signal estimation for tracking scenarios. And let's start with the first part of real data we collected for this work. It came to us from somewhere in Latin America, where they had deployed these sensors, the red dots, to find the direction and the speed of the wind using sensors that are equipped with an anemometer. I show the sensor here in the XY plane, and suppose that the anemometer gives me this angle, phi j. J is the sensor index, all right? And then you want to find the speed vector projected in x and y. So you measure pressure. This is a pressure sensor, and you measure the wind pressure, Fj on the left-hand side, at sensor j. And you want to find these vectors, Sx and Sy, plus noise Wj. That's a good old least squares problem, right? So you know the left-hand side, and you measure with an anemometer this phi j, and then you try to find Sx and Sy. However, it starts becoming more interesting if I tell you, look, you're not allowed to send me this analog amplitude fj, but I want you to send me only one bit. Then the problem becomes a little bit more interesting. So what I want you to think for a sec is that the estimation that you have been taught is given to us separately as an application from the compression field. And what I want us to think are possibly looking jointly at the tasks of estimation and compression. So this, in the more general field of distributed signal processing, raises a couple of questions. First one, why bother with these research issues, right? And the reason is that for both civilian and tactical applications, sensor networks can be deployed for monitoring and surveillance applications and can enable low-cost, fault-tolerant, decentralized signal processing to look into applications such as detection, estimation, and classification that have not been looked upon before. And what are the challenges? I already alluded to bandwidth and power. And these are the ones I will address in this talk. But the power, obviously, are dictated by the desire to maximize the sensor lifetime. So you don't want it to operate in full power. But nevertheless, as a team, all the sensors should be able to capitalize on correlated signal information that is available to the specially distributed sensors. There are a lot of problems, and we have worked under these two grants I talked to you about on. Those involve channel acquisition, synchronization issues, access and resource allocation. Where do you put and optimize your resources, at what layer and what level? But this talk in particular will deal with distributed estimation issues under stringent communication constraints. Okay? There are a lot of hybrids in between, but topologies of sensor networks fall into two categories. Either sensors with limited capabilities around a fusion center, that's what we call star topology, or ad hoc sensors without a fusion center that communicate, and they're supposed to exchange information only with single hop neighbors and somehow collectively accomplish this distributed task. All right? Now, I will touch upon, give you snapshots of our research in these two areas. And more specifically, I will look at distributed estimation with a fusion center. And my question would be, can we view and design optimally quantizers and estimators jointly to operate in a distributed environment? And for those ad hoc architectures which are developed to perform in-network processing without any fusion center, the question I want to ask myself is, can we rigorously formulate those problems and have distributed approaches perform as well as centralized approaches where data are all available at a central location, as in the case of the fusion center? These are the two questions I want to touch upon. And let me start with the first one, where I have a fusion center. Okay? And I have sensors. This is, believe it or not, a research problem that started from a final exam problem I was cooking. And I will give you exactly the final exam problem, the simplest possible scenario. So here is the model. XJ is the measurement the J sensor is recording, right? And you want to estimate a deterministic signal S, parameter S, in noise, WJ. J again is the sensor index. You know the probability density function PW. All right? Suppose you have a bandwidth constraint. So each sensor or the fusion center can only have available capital J binary observations from one bit from each sensor. All right? So how are these observations formed? Each sensor selects a threshold, if its measurement goes to the right, it sends to the fusion center 1, right? If it falls to the left, it sends nothing, on-off keying, simple, energy efficient, right? So this is an indicator function. So if you are to the right of the threshold, you get 1. The problem statement is, given these binary observations, what at the fusion center, what is the best, most accurate estimate of the signal that you can form? If I would ask you that you have the analog amplitude, the clairvoyant case of analog amplitude observations, and I tell you what's the best estimator, the best thing from any sense, if your noise is zero mean, as I assume here, would have been the sample average, right? Its maximum likelihood if it is Gaussian, blah, blah, blah. But now I cannot take so what's the best I can do with binary 1-bit things? Well, this problem is not as difficult because you can define the probability of each measurement to be 1, and this is your Bernoulli parameters. You have Bernoulli random variable here, right? And this is the probability of xj to be greater than tau c, right? That's the probability of being 1. And because you know the PDF, this probability of xj to be greater than a threshold translates to a probability of the noise to be in this range, right? So if I give you the cumulative distribution function, Fw, and the threshold, and S, you have a relationship between the Bernoulli parameters and the Bernoulli parameter Q1, which is the probability of having 1, and the cumulative distribution function. This is a monotonic creature, so it's invertible 1-to-1. So you can solve with respect to S. And amazingly, even if you have a nonlinearity imposed by the quantizer, you have a closed form. If you know the threshold, and you know the Bernoulli parameter and the PDF of the noise, you can have in closed form this S. All right? Now, we know from basics of estimation that if you have Bernoulli random variables and you take the average of the bits, that is the expected value, which in the case of 0, 1 random variables coincides with the probability of the Bernoulli parameter. So I can estimate those Q's by averaging the bits. And by maximum likelihood invariance, you have in closed form, surprisingly, an estimate of the signal parameter in terms of the threshold and the bits. So what am I telling you here? Every sensor quantizes to 1 bit, sends it to the fusion center, right? It averages, the fusion center averages the bits, applies this appropriate inverse transformation, and corrects with the threshold that he knows. It knows. And that's the estimator. Kind of interesting. The next question you ask typically when you solve estimation problems is how well you do, right? Okay, you have a way of doing it. Seems nice and economical from a communication perspective. How well can you do? So for this reason, you start deriving bounds and camera bounds that define the minimum possible attainable estimator for any unbiased estimator, right? And it turns out that for this case, you can do it. So you turn the crank, you find the camera bound in terms of the probability density function of the noise, and let's call it B of S. It depends on the threshold and the S, something that you expect, and it's inversely proportional to the number of sensors. But then my second question in this exam was, what if the noise is Gaussian, right? And if the noise is Gaussian, the minimum number of the variance that you can attain with this single bit estimator is pi over 2 sigma square over j, right? Remember, I have capital J sensors, right? So if you remember from your basics of estimation, if you have IID random variables, the variance is sigma square over j of the sample average, right? So I look at this in front and I tell you that the penalty that you pay is only pi over 2, right? So pi is 314, right? Pi over 2 is 1.6 something. So my variance increases only 1.6 something. So what's the moral of the story of what I told you? If you have 100 very, very expensive sensors, right, that quantize, that you can afford quantization to as many bits as you can imagine. You can do the same job with 160 sensors, which are extremely cheap. And that's the moral of the story. And at least as far as estimating a parameter for this task, if you want to have your gas levels estimated, for example, then I can do it in a very economical way, and I can find the best possible. Well, of course, I told you almost part of the story, because in order to achieve this minimum Kramer-Rao bound, the minimum variance, your threshold, which you might ask what's the best, value to set it to, surprisingly, the best value would be equal to the unknown parameter that you don't know. So then you say, that's a chicken egg situation. Of course, you can devise, and I'll show you systematically how to do it later on, an iterative approach, where you say, I set the threshold at 0, I find an estimator, then I put the threshold to a new value based on my previous estimator, so on. And it turns out that the performance of this depends on what I call quantization-SNR, which is the ratio between the upper and lower bound that you might have of the signal estimate. So let's say, your signal will not lie between, anywhere outside -5 and 5, right? So this is the -5 and this is the 5. And you have the variance sigma square of the noise. So if I plot the Kramer-Rao lower bound as a function of the distance of the threshold from the true value, normalized by the standard deviation of the noise, as you can see, indeed, the bound is, the value of the bound is smaller, and it's 1.6, as I told you, with the pi over 2 here, whenever the threshold is the same as the true parameter. But even if you start going away, the penalty that you pay is no more than 3/4. And more important, and surprisingly at first sight, this depends on the noise variance. So if the noise variance is very large, right? If the noise is huge, then what I'm telling you, it doesn't matter how far you are from the true value, or it matters much less. Then the first time I reached that conclusion, I scratched my head, looked back, where is my derivation? I've messed up somewhere I'm upside down because we're dying all the time to get the signal to noise ratio high, and here I'm saying that, oh, no, noise is good for you, So this is counterintuitive, right? But then I didn't find an error, and then I started thinking again. And then if you do the same, it will not take you too much time to realize that in this case, high noise is not bad. Why? Because if the noise is too high and you designate a lot of bits, then you're quantizing the noise, my friend. So quantizing it to 1 bit is much better in this case. So bottom line, this setup that I started from the exam can be generalized in various interesting directions that I don't want to bother you with. But the messages are as follows. It's possible to have low complexity maximum likelihood estimators of problems with low SNR that are typical to sensor networks. And by transmitting a single bit per sensor is possible with negligible performance loss, as low as pi over 2, relatively speaking, negligible. What I told you, when you know the noise PDF, is also possible when you know the noise PDF, but you don't know some of the parameters. So if you don't know the variance, for example. Again, the trick, if you think about it, is the following. Whenever I put a threshold, I define an equation that I can solve for my unknowns. If I have two unknowns, I can put 2 thresholds, so I can quantize to 2 bits, right? Then I can solve for more equations than unknowns. In fact, if you say, okay, then you will increase the number of bits, you can play another trick. You can ask some of your sensors to quantize to 1 bit. That gives you one equation. Some of your sensors to quantize to another bit. And still again, so you can have different thresholds. So you need different thresholds to achieve the same task. Of course, your variance will increase at that point. It will not be as small as I showed you. But the truth is, I'm trying to tell you that even if you don't know the noise, and you follow a non-parametric approach, you can solve these problems, even if they are vector parameters and vector measurements. For example, if you collect over window of time, and the conclusions are more or less the same. Just to give you a flavor, if you plot variance over number of sensors, if you know the PDF of the noise, then you have a penalty of 2, 1.6. I roughly say 2. If you don't know the variance as well, you have a penalty of 3. And if you don't even know the PDF, you can do the same job with an order of magnitude less. So again, all I'm saying, give me 100 super expensive sensors. If you give me 1,000, an order of magnitude, 900, let's say, 1,000, super chips, I can do the same job. Right? I know how to do at least this estimation problem. So an increase is expected because you're only using 1 bit from a measurement, right? You're not, but you don't expect such a small increase. And then we took this data to estimate wind parameters, and it fits the framework that I talked to you. You can write down the Fisher information matrix over this randomly placed sensors. And then again, even the 2 parameters that we were, the speed in the 2 directions, again, you see if you have clairvoyant measurements, you get the variances, the number of the sensors at this red line with the analog amplitude observations. And even if you use only 1 bit for this 2-parameter estimation problem, your penalty is really small. Then we got ambitious, and we said, okay, I know how to do, how to estimate parameters. Let me try to see whether I can do the same things to estimate a signal that varies, right? And track things. So suppose you're trying to estimate your standard Gauss-Markov linear model. That's a common model describing the state, right? The state is common. Imagine a tracking problem, if you like. Suppose a UAV or something that you want to monitor goes over a bunch of sensors, right? The state is common. Each sensor gets a measurement in noise. And sensors exchange information bits Bn in a round-robin fashion. Okay? So the target flies over here. So suppose Professor Krim is sensor number 1. In the first slot, let's define a protocol for scheduling. In the first slot, he's going to do something and broadcast to his neighbors the bit. Then if you are sensor number 2, you will take over in the next slot, and so on and so forth. That's why this one is envisioned. And suppose that we have a one-to-one mapping between the time slot and the messages. So the issue is to carry out decentralized sensing and estimation based on quantized observations.
So you do have master plan?
Yes. Quantized Kalman filtering is my objective for distributed tracking applications, and I want to have scalable communication cost, right? So this is the busiest slide of the talk. There is a discrete time state space model, the usual one that you see in the Kalman filtering. S is the state, X is the measurement, A is the state transition matrix. Usual assumptions on the noise Gaussian. The point is that I want to carry out the minimum mean square error state estimation problem using quantized data. So what you're going to notice is that this conditional expectation, which is the optimum estimation, is conditioned not on the observations X, but on the binary observations from 0 up to n. That's the difference. Of course, you can write down the thing in integral form, but you cannot even think of estimating it numerically because the number of states could be huge. The numerical integration is out of the question because this PDF is non-Gaussian. If you attempt to go a la Kalman filtering, you start with the Bayes rule and you try the a posteriori density P of S given B0, you split it into the previous one and the current one. Again, this density that I have in red here cannot be available in closed form. You understand, you have basically this quantizer introduces a nonlinearity, you destroy any Gaussianity you have. So you cannot carry out this form in that way. However, our idea was the following, and we came up with a very surprising result. If we fit a Gaussian PDF to this problem, so if a fortiori we say, okay, this guy can be approximated by a Gaussian, right? With the mean at the predicted version and the covariance matrix as such, it is of interest to see how far we can push it and how much we pay for this approximation. So you can derive a recursive algorithm, which is very similar to the Kalman filter in a distributed fashion. In fact, because the state is the same and the model for the state is linear, right? Then if you take the conditional expectation, the predictor is linear. So you express the predictor in terms of the filtered estimate of the Kalman filter. And likewise, you have the covariance obeying a similar recursive equation. The difference is in the corrector. So the corrector, which is the estimate of the signal S given n observations, is equal to the predictor that you found as before recursively, plus a gain kn times a function of the binary observations. Now, what is this function? This function is written here. Is the difference between the measurement x of n and the predicted measurement, which is what we call innovations, right? So this difference is the innovations of your measurements. And then, how do you form the binary observations? You just take the sign, plus minus, right? So it's like, again, a 1-bit business, right? 1, 0, here is 1 minus 1. And look at how beautiful interpretation you can have. Where do you quantize? So you have the predicted version of your observations, in a way, serve as your threshold that was fixed before, right? Now the threshold is time varying, right? Because the signal is varying. So depending on, it's roughly speaking like saying, okay, this thing is coming toward me or away from me, roughly speaking. That's the innovation. That's the plus minus. Okay? Now, once you understood how you can solve this problem with what I call soy KF, with a Japanese flavor, right? Sign of innovations is the abbreviation. Okay? Or the scent of innovations, if you like. Scent of a Woman is the well-known movie. When the Kalman gain turns out to have a factor 2 over pi. All right? And then you can say, okay, why should I restrict myself now that I understood the trick? Why should I restrict myself to 1 bit? I can iteratively quantize. And roughly speaking, with the picture, I don't want to show too many equations, but at the very beginning, you decide whether your measurement is to the left or the right, and then you do another iteration within that interval, and you add more and more bits. So it's like iteratively you add bits. The most important part that you want to ask is, how is the performance of the Kalman filter? Then you write down your Riccati equation, steady state, blah, blah, blah. And I just want to tell you that what matters out of this is this red term. This is a recursion that shows how the covariance of the state evolves in time, right? So how you find the performance of it. What matters is this red term. And in the red term, M is the number of bits that you are designated to every sensor. You are designating to every sensor. If M equals 1, what you notice is that 1 minus 1 cancels, and 2 over pi, you have the pi over 2 effect that you had before. Surprising. If you send M to infinity, so you have infinite bits per measurement, then everything, this is 1. So you get the clairvoyant Kalman filter. Analog amplitude observation Kalman filter. And you have the gamut in between. So what's the punchline here? You tell me, look, I have the sensors, you know, I want them to live that many days, right, or months. I can afford that many bits, all right? Then I can tell you, okay, the accuracy that you're going to get in your Kalman filter is that much, all right? But the accuracy in your resolution that you will discriminate targets is from 1 meter to 3 meters. The other way around. You tell me, no, I want 1 meter. Then I will tell you, well, then you need 4 bits per measurement, and they will live that many days. These are the types of statements I can make. All right? And incidentally, this work recently was invited in the special issue in the 50 years of Kalman's invention in the Controls magazine. But let me give you some simulations to see what is the story here. This is from two thermal sensors, mean square error versus time. This is the clairvoyant Kalman filter, and this is what you do with 1 bit. And this is what you do with 2 or 3 bits. Again, you see a saturation. So the benefits if you go down, and this is meaningful because if you remember, this one is exponential. So the gains that you get by adding 1 more bit diminish. So bottom line is that 2, 3 bits are typically very good, right? So that's the message I want to convey. And then you go to become more, excited, and you say, okay, let me do something that's non-linear, right? And you know that whenever you do tracking and localization, because the distance is the square root of the coordinates, right? And you get log power things, the transformation is non-linear. So you have to live not with an ordinary Kalman filter, but what we call extended Kalman filter, right? So sure enough, if you look at the target tracking experiment, position x1, x2, the magenta circles are the sensors. This is what the target does, right? And the bottom line is that if you do Kalman filtering or extended Kalman filtering or using the full-blown analog amplitude observations and the Kalman filtering with single sign of innovations type of inexpensive sensors, a lot of them, how many, 100 sensors, then the performance can be virtually indistinguishable. That's the message that I want to convey. And these were simulated data. This is my collaboration with this robotics expert. So there were 2 robots. These are real data, actually. 2 robots that were somewhere in a cave in a country I don't want to talk about. So they have a GPS outside. They go inside. They don't have GPS. And they have to rely on collaborative localization, right, to find themselves. Then they have a gyro for heading, odometer for velocity, and measured robot-to-robot distance. There are the blue robot, let's call it, that follows this trajectory, and the red robot. And then they stop at several points and they exchange measurements, distances. So you can formulate a problem like the one that I showed you earlier, and the state contains the positions and headings of the robots. They predict with the constant velocity model and update with the velocity, heading, and distance. And here I want to compare the extended Kalman filter and the iteratively quantized extended Kalman filter. So I got this real data. We got it with my collaborator. And I show you here the extended Kalman filter is the blue. And using only 3 bits out of it and communicating only 3 bits.
But if they don't have a GPS system, how do they know the positions to convey the information?
Because they exchange between themselves. They have a gyro, so they know their heading, right, the bearing. Mm-hmm. And they have an odometer, okay, so they know. They can do dead reckoning. But the problem is well known that if you let every robot follow a dead reckoning, then eventually it's going to diverge, right? So it's like I tell you where you started. So they start with GPS outside, so they have a good GPS fix. So, and then I tell you, close your eyes and start moving. Because of your errors, will accumulate. Yeah. But at the very beginning, you are perfectly fine. But the proof here is that whenever the collaborative localization, the premise of collaborative localization, is that by exchanging information, their accuracy improve by 1 over the number of robots that collaborate. So, in other words, if I lose my way when I'm on my own, after 10 meters, if I have 10 robots, then I will lose my way after 100 meters. That's the premise. So that's why the collaborative. And this is, again, the 3 bits virtually identical trajectories between the 2, you see. And the same for robot number 2. And this is to show exactly what I was just alluding to. If you look at the error in the x direction, and then you compare the dead reckoning, so I'm going on my own, as opposed to I use an iteratively quantized extended Kalman filter with minimal communications, then the dead reckoning increases the inaccuracy in the distance in the, whatever it's, the axis here is time in seconds, right? So in, let's say, 400 seconds, if you don't collaborate the way I described, then you have an inaccuracy by 5 meters in the x direction. And if you do collaborate, you are almost on target. And that's the message, that you can really do that only by exchanging 3 bits. This is where quantization and estimation, blend nicely together. The rest of the remaining time, I want to touch upon the second question, where I don't have a fusion center. And first of all, we have to understand what are the advantages of it. If you have a fusion center, the scaling issue is a problem. And in other words, the sensors that are remotely located to access the fusion center, they need to spend much more power, right? Furthermore, if you talk about the tactical application, if the enemy brings down the fusion center, then you isolate the point of failure, right? So your whole network is dead. So you prefer to have these tasks be performed without a fusion center in network. And what I'm going to talk about is this new approach that we have worked on, where sensors consent to informing the desired estimate. And the premise here is that I only communicate with my neighbors, and I allow the challenge links to be non-ideal. So I capture quantization and receiver noise as an additive noise between links, and that are allowed even to fail. But I will look at the analog amplitude observations in this part. The system setup, you have J sensors, Nj is the neighborhood of the Jth sensor. The observations are correlated with S, the signal of interest. And somehow, I communicate with neighbors, neighbors talk with neighbors, the gossiping goes all over, and then the information percolates to all sensors in the network, and they can form the estimate. Yeah?
How do we know who the neighbors are?
This is something that, in this particular talk, I assume solved. This is a well-known problem. Neighborhood discovery is called, and there are a lot of protocols that can do that. But I'm not dealing with this. So suppose that I know my neighborhoods. You can think of it, one easy approach is, this is how much power I can spend, right? And I look in this disk of power that I can be heard by, who acknowledges my number, right? Then this is my neighbor. That's one thing, right? All right. Now, let me talk to you about an exciting result that started, actually, this is rooted very firmly in distributed optimization that was pioneered by Bertsekas and Tsitsiklis in the 80s and 90s. There's a huge difference there, but these guys are experts, obviously, in optimization. They were looking at parallel processing problems, where you distribute a difficult problem into pieces so they can it can be solved by not as powerful processors. But these things are wireline. So what my group has done, has taken a lot of their ideas, but we try to see their implications in a wireless setting and whenever you have estimation problems rather than minimum path routing problems, for example. Things of dynamic program, distributed routing problems, shortest path routing. So here is how the issue started with Shao and Boyd from Stanford, when they noticed something very simple. Suppose I want to solve this problem. Every measurement, like my starting point, every sensor has a measurement, and somehow we're trying to find the average, right? To consent on the average. All of us. In a very magic way, if I may say, they proposed this recursion thinking in terms of dynamical systems. All right? So they say that every sensor receives estimates from its neighbors. So I belongs in the neighborhood of J. So they say the value of my sensor at point K plus 1, this is sensor J, is the same as the value of the sensor J at point K plus a linear combination of errors between sensors I and J, me and my neighbors, right? Now, if you collect all of this, because this transformation is linear, you can write down a vector linear equation and study its convergence. And if you select, they proved that if you select these weights, gamma, in an appropriate way, it's possible that this thing consents to the average. That's their claim. Think about it. If everybody has the same value, this term is inactive, right? So consensus has occurred, and this iteration stops. Right? Well, it turns out that you want to, in order to do that, you have to choose carefully this matrix gamma, and the entries depend on the number of neighbors that you have and so on and so forth, but it does not require knowledge of the global network topology or the graph. However, in order for them to achieve that, the matrix gamma must have an eigenvalue equal to 1, which is a blessing and a curse. The blessing because it converges to the average, it turns out, and the curse because if you happen to have noise somewhere in the loop, then this noise will go out of the roof with an eigenvalue 1. So our work was basically to try and understand how can we cope with noise, and second, how can we solve more general problems that do not have only to be confined to averages. All right? So this is one slide of the general framework. So we said, suppose that you have two sensors and you want to minimize a cost function that is decomposable in the measurements, right? Think of the mean square error here. But this common S, which is the signal of interest, couples the two terms. So you cannot carry out this optimization problem, all right, in each sensor. Every sensor alone can carry out one part of the pie because it has that measurement, right? But this estimate is not the same as the centralized. So our idea to formulate the problem rigorously is this. That's the core part of the idea. We look at the centralized objective, and instead of having one unknown, which is common and couples these two, we're going to postulate two unknowns, S1 and S2. All right? But we're going to turn this unconstrained optimization problem into a constrained optimization problem and force these two estimates to agree. So if I tell you, you play with your own data, you do whatever you want, but at the end of the day, what you're going to give me has to be the same as her estimate. This is a way of enforcing consensus and enforcing you to collaborate. You have to tell her at some point, I mean, what did you find? All right? So ours should be the same. I mean, I cannot give him 3 and we give him 4, and we have to give him something that's the same. So that enforces the communication and collaboration protocol. So let's start with, because we are running out of time, with the problem of maximum likelihood estimation, for example, where I write it as a minimum because optimization theorists like to write everything as a cost rather than as a reward. Minimum of the minus, subject to this constraint, right? Consensus constraint. So I associate a local estimate of the jth sensor, the Sj, and I impose consensus through the constraints. Then I borrow a method developed by Bertsekas on the alternating direction method of multipliers for this particular problem. And what you do in this case, in my problem, you associate a Lagrange multiplier with one constraint and you update it in each sensor. And here is how I can solve the distributed maximum likelihood problem. I run a recursion, which is like LMS of the Lagrange multiplier at every sensor. And I solve a local optimization problem, and I can prove that if you let me iterate with my neighbors, provably I can converge to the centralized maximum likelihood. As if, in other words, all the data were available at every sensor. Right? So this is how it works. It's like, you receive from your neighbors their current estimates, and then you are updating the multipliers and broadcast the multipliers. Then you receive the multipliers, and then you update your estimates from your neighbors. All right? So the multiplier, in a way, is how far we are from consensus. That's what it signifies, if you like. Of course, you can do much easier things than what you saw. If you have distributed least squares and best linear unbiased, then the equations look much simpler. All linear recursions, low cost. You run 2 recursions per sensor, and probably you achieve consensus to the optimum solution. We have done convergence, proved that it converges in the mean, and it has bounded covariance even in the presence of noise. Then we analyzed communication and computational complexity is p square. P is the size of the estimator that you're after, and the communication is linear in the size of the vector you're trying to estimate. We have ways of trading off convergence for steady state error, and it's fairly fast relative to what is out there. You can converge in less than 300-400 iterations with 60 sensors. Noisy links, what is out there grows unbounded, and we converge. It is possible to extend these ideas that I just told you, not only for static deterministic parameters, but also to develop adaptive algorithms. And we have been able to develop what I call distributed least mean square error algorithm. So again, this is your classical LMS starting point. But here, notice that I am designating one variable per sensor, and I'm adding a constraint. So there are two key steps. You use again the alternating direction method of multipliers, and you use stochastic approximation idea, Robbins-Monroe-like, to develop these distributed versions. So you have a recursion to update multipliers per sensor, and you update the local variables. The blue ones are pretty much like what you would have done in LMS, but you have another term, red term, that basically is influenced by the consensus, the effort to consent with your neighbors. And again, the algorithm is more or less the same. We have done stability analysis. So provably all these things converge as they're supposed to. Under mild assumptions, basically you need bounded moments and proper step size selection. And you guarantee, of course, that if your parameter, if there is noise similar to LMS, you can guarantee a convergence to a ball. So you have misadjustment, right? You cannot converge to, because you have stochastic approximation algorithms. But if, of course, there is no noise, you will converge almost surely to the true solution. Now, this is the most general results that are there for distributed algorithms with correlated observations. Just to give you a sense, learning curves for the adaptive algorithm versus the iterations. So if you have everything centrally available without intersensor communication noise, you have this learning curve out in 100 or 250, 300 iterations. The distributed may take 1,000 if you have the same noise and you have noise between intersensors, so it's slower a little bit. But definitely, it is much better than the local, meaning if you were trying alone to track something, you can see that the error is significantly higher, and after even 250 iterations. And we've checked it with tracking. This is time-varying parameters versus iteration index. And we show here the different levels of communication noise. But you see, even in high communication noise, you more or less track the envelope correctly. It's about to wrap it up. I touched upon two subjects on distributed estimation using sensor networks. In the first subject, I looked into sensor networks that are equipped with a fusion center. So I talked about sensor fusion basically problems. And I touched upon designs of quantizers and estimators that can incur minimal loss in performance at low signal-to-noise ratio in particular, and showed how to develop a quantized Kalman tracker that has scalable communication cost. So it can communicate with neighbors with 1 bits or 2 per exchange. We have also done a lot of work in principal component analysis for dimensionality reduction in a distributed fashion, because the idea sometimes, another idea that you can end up with a manageable communication cost is to start collecting data, right, at different sensors over some time horizon, and then suppose you have collected 100 or 20, 1,000 observations, then you can apply a dimensionality reducing operator to squeeze out the most significant part of it, right, and boil down from, let's say, boil down your 1,000 by 1 vector to 5 by 1 type of vector, and then communicate that one. I didn't touch upon this, but that's equally interesting. I also talked about distributed in-network estimation approaches, and which I demonstrated to have resilience to receiver and quantization noise. We can tackle any type of estimator. We have developed even Kalman filters and smoothers around this, and can handle correlated observations. I already mentioned that we can handle more complicated model-based approaches for dynamical processes that are suggesting a distributed Kalman filtering based on single hop exchanges again. And on that note, I'll be glad to answer any questions you might have on this one. Thank you. Yeah.
Any questions?
Yeah, please go ahead. You said you want to.
Yeah. Okay. I'm trying to understand the example you gave for the robots. There are 2 robots, blue and red. That's supposed to be example for a fusion center case. There's a fusion center for that case.
No, this one is basically, there's no fusion center, the exchange between the 2 of them. But they're just 2. One can serve a fusion center of the other, you can say.
Oh, okay.
So because there are only 2, right, in this experiment, we had real data for 2 robots. All right? So their performance improves relative to dead reckoning by exchanging measurements between the 2 of them. So I tell them, suppose you are the other robot, I tell you, I'm here right now, and I'm that far from you, and you tell me the same thing. And I use it in my state vector to, you serve for me as a landmark, basically.
Yeah, well, I was trying to see a fusion center there. So the other robot serves as a fusion center for another one.
You can think of it that way, correct.
Yeah, thank you.
You're welcome.
Any other questions?
Well, the point that I was trying to illustrate with the robots was that there's a lot of interest in the robotics community, at least, in collaborative localization. And both NASA is pushing that direction because they send robots up there, and the Army is interested, the Navy, they have underwater robots. But in both cases, caves and underwater, you can only get a GPS fixed at the beginning. Then you have to, that's why collaboration is extremely important when they go in a GPS blind zone. It's extremely important to communicate. And the purpose there was to illustrate that I don't need to communicate all the measurements. If I do it right and I run my Kalman filter the right way, as we have demonstrated, then 2-3 bits are more than enough. That's the real essence of this experiment.
Any other questions?
Yeah.
If you substitute, say, 100 expensive sensors with, say, 1,000 cheap sensors, Would there be any criteria for power trade-off? Like, would 1,000 sensors consume more power as compared to 100 sensors? Have you looked into that aspect?
Yeah, we looked at it. I didn't cover. We looked a lot on power consumption ideas, and this is where we used this approach. In particular, we solved the problem. Okay, you know that in every communication system, point-to-point communication system, Shannon's optimality theorem says that I can design the source coder separately from the channel coder, right? So I can optimize one in the limit, at least. The thing is that there is a presumption there that you have a powerful code that you will correct any problem related to noise. That's why people, when they do source coding, they never talk about noise. Because they say, okay, my channel code is going to take care of the noise, right? That's the presumption. However, you cannot do that in a sensor network. So what we have tried to solve in this bullet here that I touched upon, but I didn't talk too much. If you want to, I have slides offline. I can show you. The problem formulation is the following. You have different sensors, right? And suppose that you can tell me this sensor has that much power, this sensor has that much power, right? Then I will formulate a problem where I minimize the error in estimation, for example, subject to power constraints per sensor, right? And how much I need to reduce thereby. Because you can imagine that if all of us collect 100 measurements, right, and we have XYZ power, the power may not be enough for us to send all the measurements. That necessitates a smart dimensionality reduction. So you squeeze a big vector into a small vector so you can fit your power requirements as well as deliver your estimation performance constraints. So that's what we have looked at. So you can impose power constraints. That's the answer. Yeah.
We have time for one more question. I have a question.
Sure.
It seemed to me that intuitively and it wasn't apparent, at least from the equations that I was able to grasp, the spatial correlation of the sensors never appeared explicitly, but it seemed to me that it should, somehow, somewhere.
Yeah, I went fairly fast on that. Okay. The reason that it didn't show up in the things were that here I assumed conditional independence in order to write this log likelihood as a sum of the likelihoods, right?
Yes.
So indeed there is no. So that's why it didn't appear. However, you can have least squares and LMMSE, and here, for example, there is a covariance that has to do with sensors xj.
Where are you pointing? I can't see your laser.
This is here.
Okay.
You can have a norm. For example, this is a least squares problem, right? And the norm can be a weighted norm.
Right.
So the weighted norm will contain the correlation among sensor information. And then you can take into account this correlation. This is one thing in this context. In the Kalman filtering context, you can take it by updating your covariances. When you update the covariance, you update the correlation among different sensors. Now, I should have had the LMMSE. Okay, let me see. In the adaptive case, yes, but it depends on the regressors here. The regressors capture the local correlation. If I go to the Kalman, I should be able to give you more. Oops. What's up? All right. Yeah, this is, if you look at non-stationary dynamical systems, right, the correlation here, you are uncorrelated in time, but you are allowed to be correlated in space, right?
Right.
QN can be uncorrelated, correlated in space. I don't know why this one does not work. hoping to give you a little bit more. So. Oh, this one is not helpful. But as I mentioned before, I don't know why it is delaying this one. Probably because the other one takes time to load. But the one that I showed you incorporates the noise correlation, not the first one.
All right. Well, let's thank our speaker again.
Thank you.